Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course. This video lesson is broken up into 3 different parts. First, we're going to be briefly talking about carbon-13, nuclear magnetic resonance spectroscopy, C13 NMR. Next, we'll be going over 2D NMR, two-dimensional nuclear magnetic resonance spectroscopy. And then finally, a different but very popular technique in the medical field, going over the fundamental background of the physics and chemistry behind magnetic resonance imaging, or MRI. So we'll start out with carbon-13 NMR. So the development of this instrumentation technique, this type of spectroscopy, lagged behind proton spectroscopy or proton NMR spectroscopy, primarily because of 2 problems. One is the particularly low natural abundance of carbon-13. This is only about 1.1%, and the resulting weak signal that's associated with that. And so the second problem is that the magnetic moment of carbon-13 is considerably smaller than that of the proton, which causes the population of the higher and lower nuclear spin states to differ by much less than that for proton NMR spectroscopy. So taken in combination, these 2 factors mean that carbon-13 NMR signals in natural samples, and so those are those that are not artificially enriched with carbon-13, are only about 10 to the minus 4 times the strength of proton NMR signals. Now, as with proton NMR spectra, the splitting patterns in carbon-13 NMR spectra are also explained according to an N+1 rule. So you should refer back to the proton NMR spectroscopy video for a full description of splitting patterns in proton NMR. But the N+1 rule is slightly different for proton NMR spectroscopy versus carbon-13. So because in natural abundance only 1.1% of carbon atoms are carbon-13, almost all of those atoms in a molecule have a magnetically inactive carbon-12 next to them. So remember that carbon-12 has a nuclear spin quantum number I of 0, and carbon-13 has a nuclear spin quantum number I of 1/2. And so a nucleus that has a spin quantum number of I has 2 I plus 1 spin states. That means that carbon-12 only has 1 spin state, so it's magnetically inactive. Carbon-13 has 2. So as I was saying, because pretty much all carbon-13 atoms in a molecule are going to be next to these magnetically inactive carbon-12s, the N+1 splitting rule doesn't have to do with adjacent carbons. And so that's why splitting due to interaction between the spins of the nuclei of carbon-13 and carbon-13 atoms is not normally observed. Normally, the signal from a carbon-13 nucleus is split by the hydrogens that are bound to it. But it still has the same formalism of the N+1 as the proton NMR spectroscopy rule. So if a carbon-13 atom has N hydrogens bound to it, like this atom, the signal is going to be split into N+1 peaks. And so the carbon-13 signal associated with this atom is going to be a quartet because there's 1, 2, 3 hydrogens bound to it. Now this is also useful because the carbon-13 proton signal splitting provides important information about the number of hydrogens that are bound to each carbon. A disadvantage, however, of this type of signal splitting is that the coupling constants are usually between about 100 and 250 hertz. And so this is a pretty common range. And so at 75 megahertz, the radio frequency, those types of coupling constants at magnitude corresponds to chemical shift differences of 1.33 to 3.33 ppm. So what that basically means is that the overlap among signals can be significant and that splitting patterns are very often difficult to determine. Additionally, there are smaller but sometimes significant couplings from hydrogens that are not directly bound to that carbon but are separated by 2 or 3 bonds. So this extensive splitting causes the already weak signals of carbon-13 to split into many smaller peaks, that can be easily lost to noise from the instrument. And so because of this reason, the most common mode of operation for carbon-13 NMR is something called a hydrogen decoupled mode. And so that's something that we'll go over in just a couple of minutes. So first we have shown here the carbon-13 NMR chemical shifts of different representative functional groups of a molecule. Now these values are approximate, and you'll be able to compare with the proton NMR spectroscopy correlation tables like this that the regions of the chemical shifts are significantly different. First, you can notice how much wider the range of chemical shifts are for carbon-13 versus proton NMR. Now, most chemical shifts for proton NMR fall within a very narrow range of 0 to 10 ppm. However, those for carbon-13 NMR can cover the range of 0 to about 220 ppm. Now, because of this expanded scale, it's very unusual to find any two non-equivalent carbons in the same molecule with identical chemical shifts. Most commonly, each different type of carbon within a molecule has a very distinct signal that's clearly resolved from any other signals. Now, one thing that you can notice here is that the chemical shift of carbonyl carbons is quite distinct from those of sp3 hybridized carbons and of other types of sp2 hybridized carbons. So the presence or absence of a carbonyl carbon is very easy to recognize in this type of NMR spectrum. Likewise, the signals from sp2 hybridized carbons fall within a very distinctive range of 100 to 160 ppm. So let's look at an example now. Here we have a carbon-13 NMR spectrum for 1-bromobutane. As you can see, compared with the proton NMR videos that we have, the chemical shifts are vastly different, and so for proton NMR, again, it's usually in the range of about 0 to 10 ppm, and here we have it very far extended. Now, if you compare with the chemical shifts that we just showed for the different representative groups, it's not surprising here that this only goes out to about 40 ppm compared to that, for example, for carbonyl carbons that extends far past 100 ppm. Now, importantly also here is that this is a hydrogen decoupled carbon-13 NMR spectrum. So in hydrogen decoupled mode, the sample is irradiated with two different radio frequencies. The first radio frequency is used to excite the carbon-13 nuclei, and so exciting that nuclei means, again, spin flipping. The second is a broad spectrum of frequencies that causes all of the hydrogens in the molecule to undergo rapid transitions among their nuclear spin states. And so on the time scale of the carbon-13 NMR spectrum, each hydrogen is in a time average of the two states, with the result that the proton carbon-13 spin-spin interaction is not observed. And so the term for this process is spin-spin decoupling. So in a spectrum like this, a hydrogen decoupled spectrum, all of the carbon-13 NMR signals appear as singlets. And so in this case, we have 4 singlets for the 4 different carbon atoms in this molecule. This fifth one here, all the way at 0 ppm, is for our reference molecule, TMS, just like proton NMR. So looking at this spectrum, we can see the number of distinct peaks that you have corresponds to the number of carbon atoms. And sometimes, similar to proton NMR spectroscopy, the integration of each one of these peaks would give you the number of hydrogens for each of those equivalent hydrogen types. However, there's a caution here with carbon-13 NMR because of certain complications, including the long relaxation times of carbon-13 nuclei. A lot of times it's not really possible to determine the number of carbons for each type by integration of these signal areas. And so, for example, you can see here there's only one type of, or one single carbon for each of these different types that we have here. And so theoretically each one of these 4 peaks should be the same height. or the same integration area, but sometimes they're not, and so you can't always trust that. Now we can do an example where we want to predict the number of signals in a proton decoupled carbon-13 NMR spectrum for each of these compounds. And so proton decoupled, again, we're not looking at the splitting for these guys, just the total number of signals. So the molecule on the left-hand side, this is methyl acetate. For this molecule, we're going to have 3 different peaks for each of these different carbon atoms. Now, the chemical shift of this carbonyl carbon is going to be very far shifted compared to the other 2, which may be a bit closer together. The molecule on the right-hand side, 3-pentanone, is also going to have just 3 signals. So we have to look at the number of distinctive carbon atoms. And so here we have 1, the carbonyl carbon. It's going to be the most shifted, the largest chemical shift. This carbon and this carbon are identical based on symmetry of the molecule. Likewise, so are the end methyl carbons. And so we're going to have a total of 3 different signals. Now, another type of carbon-13 NMR spectroscopy techniques is called depth spectroscopy, or distortionless enhancement by polarization transfer. So this is an NMR technique or method that's used to determine the presence of primary, secondary, and tertiary carbon atoms and differentiate between those. So this is a different technique than the completely proton decoupled carbon-13 NMR. And so in that case, remember, a radiofrequency pulse is used to excite the carbon-13 nuclei, and then a broad spectrum of frequencies causes all of the hydrogens to undergo rapid transitions and time average between the 2 spin states. So this is different. The depth method uses a complex series of pulses and both the frequency ranges to excite the protons, spin states, and the carbon-13 atoms in slightly different ways. And so there's what's called a 45-degree pulse, a 90-degree pulse, and a 135-degree pulse.